I will talk to you about N-differential graded algebras. This is a joint work with Mauricio Angel and also Jaime Camacaro. That I don't see it here. It should be in this reference, Jaime Camacaro, but it's not there. And well, first of all, I will give you the definition of differential complex. This definition has been introduced several times and then forgotten. It was, I think, originally introduced by Meyer, and then but it became, at least for me, more known with some paper by Kapranov. So an N-complex is just a C-graded vector space. You can write it like this, and you have a degree 1 linear map such that if you take the n power of the differential, you get 0. Okay, so usual definition, we have a complex is n equals 2. So any result that we get for n differential for n complexes with n equal 2, we should recover the classical case. So now the question is how you can write, you can incorporate this definition of n complex with a product, with an algebra. Okay, so I think it was introduced by Kerner, this definition. I also read it from Dubois-Viollet and by Kapranov. And then with this definition, you start by fixing an nth root of unity, primitive nth root of unity. And then you have your differential of degree 1 also. You have your nilpotent condition, d to the n equal to 0. And you modify your Leibniz rule for this q deformed Leibniz rule. So in normal Leibniz rule, you have -1 here, you get q to the n power. So this is the definition of a q differential graded algebra. Okay. Now, so you see that in this definition, you are modifying both conditions in the usual definition of a differential graded algebra. So you modify your nilpotent rule, but also the Leibniz rule. So the question that we ask is that whether it's possible to find examples when you only modify this condition and you keep the usual Leibniz rule. So the advantage is, of course, that if you do that, then you can make better contact with differential geometric constructions instead with the Q. Of course, in this conference, we like very much the Q deformations, the quantum group, and so on, the Jackson integrals. But for standard differential geometry, it's much better to use the -1. So the question is whether you can do this, find such a definition where you only modify this condition. You get the differential to the n power equal to 0, but you keep the usual Leibniz rule. And so that was the question that we posed, whether there are examples or natural construction of these sort of things. And actually, when we were starting to work about this, the question was, well, where are we going to get the examples? And then the only thing that we can think of at the time was using deformation theory. So is it possible to get some differential algebra and deform it to some n-differential algebra? So that was the question that we were trying to ask. So let me first justify this, the definition of n-differential graded algebras from the categorical point of view. So you can construct a category where you put all n complexes for all n. So you can choose such a category. And this category, you will find a monoidal structure. So you have two complexes, say you have an n complex and then n complex. You tensor them, then you get an n plus n minus 1 complex. So as you can see, the differential N-differential graded algebra or nilpotent differential graded algebra is a category of monoids inside that category. So in this sense, it's a very natural definition from the categorical point of view, and automatically you get a symmetric monoidal structure in that category. So let me then try to give you some examples of N-differential graded algebras, then show you, give you the first step towards a theory of the formation of N-differential graded algebras. And if I have time, I give you two applications to construct N-Lie algebroids and N-infinity algebras. In this talk, when I talk about the formations, I'm talking about the formations of the differential, not of the product. It's very important. So let me give you first example. Is the example of what I call N-flat connections. This is very geometric example, very simple geometric example. You take, say, a trivial vector bundle, a connection on it, and then with this you can construct the covariant derivative of this object. Then we have the following proposition. If you take the differential forms with values in the vector bundle, then this will be a 2n differential graded algebra if and only if the curvature is what we call n-flat, meaning that the curvature to the power n is equal to 0. So anytime you get some bundle with this condition that the curvature is to the some power is equal to 0, then this becomes a 2n differential graded algebra. So here you have a very concrete example. You take the Popper functions, compute the curvature is not 0, and then when you square it, the curvature is 0. So you get this an example of a 4 differential graded algebra. And the same construction can be generalized in the following sense. You take this will give rise to 2n differential graded algebras. You take a Riemannian manifold. You decompose assume that you can decompose the tangent bundle into two bundles, two sub-bundles, and the G, the metric, is flat on B. There is no curvature along the B directions. Then you can show that this will be a 2n differential graded algebra for n greater than dimension of A. Then this is the different sort of examples. You fix an integer n bigger than 3, and then I will construct a differential graded this number differential graded algebra on this thing that I call differential form of depth n. Okay. So I will tell you what is this in a minute. So, you have some number, and this will be it will be a differential graded algebra with this nilpotent exponent. So how I do define this? Well, first I take coordinates on Rn, and then I take like the differentials of these coordinates. But usually, of course, we only take d, and then d squared is 0. But here I go to the power n minus 1. Okay. So I can keep doing differentials. They are not 0. And the d0 is the standard variable. And then I do this algebra. I do the algebra, the polynomial algebra. These are polynomial differentials generated by these variables. Every time I apply some d, the degree increases by 1. So xi is degree 0, xi is degree 1, and so on. And then I do this, I divide by this ideal. So if I have two differentials along the same dimension, the product is 0. But I could have differentials along different directions. Okay, and well, then I define the differential. We could say a generalization of the RAM differential as usual. If I plug in a derivative, I just increase the number of derivatives, and for the last one is 0. Okay, And then, well, you check that this you obtain is n with this number differential graded algebra. Okay, and the proof is rather simple of this fact. I mean, it just comes from the fact that this, if you get R and instead of Rn, if you apply this construction to R, then you get n differential graded algebra. And you can check that if you have, like I said before at the beginning, if you have an n differential graded algebra and you have a p differential graded algebra, then the tensor product becomes as n plus p minus 1 differential graded algebra, and then you use the fact that these forms on Rn are the same as the tensor product of the form on each direction. Well, this construction can be generalized and applied to every affine manifold. For every affine manifold, you can construct this algebra in algebra or differential graded or this differential graded algebra of forms, differential forms of depth n. Okay. So and also there is this construction by Sullivan's that allows you to associate differential forms to simplicial sets. Well, you can generalize this construction and apply it and construct differential forms of depth n in any simplicial set. Well, this is a discrete version of the previous example. This is not exactly an example, but in the sense that the Leibniz rule is also modified, but it's similar in feeling. But I don't think I have the time to explain many details. But you can discretize everything in the previous example, and this is generalized the difference forms constructed by Seiberger. So you work with this, and very much the same as before. Well, there are some formulas there. I don't think I have the time to give many details. But in any case, they give you an example, that of course, because I'm now using instead of derivative difference, then you don't get exactly the Leibniz rule, but some twisted version of it. And again, you can generalize this to simplicial sets. Now, this is how we got to think about examples. First, like I told you, is by deforming the differential. So originally we were thinking, well, take a differential graded algebra and deform it to some n differential graded algebra. So as you know, if you take a differential graded algebra and you want to deform the differential by adding some element to this, so you write you want to know if some d plus e is a differential. Suppose you have a standard differential algebra, then you want to know if d plus e is a differential also. Then this e has to satisfy the Maurer-Cartan equation. So what we have to do is to find a different or a generalized equation that tells you when you can modify an n differential graded algebra into a m differential graded algebra by adding some quantity, by adding some derivation, some linear map. So you have a n differential graded algebra, you have a map of degree 1, and derivation, you want to know when this is a m differential graded algebra. Well, there is some combinatorial constructions. I give you some details, not too many. I don't have. So there are some constructions there, some notations. This is good to keep in mind. If I apply the bracket, so if I have some linear map, I apply the bracket with the differential, then I use this notation. Well, some conventions, some vectors, more conventions here, and this is some restrictions that appear naturally in the construction that comes now. Well, and let me just probably give you the answer and then go back. And then the point is that you can construct some equation that I call the NM Maurer-Cartan equation. It's given like this. If you put n equal to 2 and m equal to 2, you get the usual Maurer-Cartan equation. And well, the fact is that these coefficients here are written like this. So you have these polynomials, say, in the e variable, And we have some coefficients, and these coefficients can be constructed combinatorially using these lattices and some kind of quantum mechanical, discrete quantum mechanical construction. You can find some lattices. They count some kind of path in some lattices with some weights. These I'm writing in these slides, and then you get this Maurer-Cartan equation. Okay, this is generalized Maurer-Cartan equation. So I give you a couple of examples. They are not so easy to write. For example, this is if I have a 3 differential graded algebra, I want to deform it into a 3 differential graded algebra by adding some E derivation. This is the equation that should be satisfied. And this is I call this the 3, 3 Maurer-Cartan equation. And if I want to deform a 3 differential graded algebra into a 4 differential graded algebra, then this is the equation that we have to check that holds. And again, in this business, it's always very useful to discuss the infinitesimal case. So when you have a deformation, d plus te, where you assume that t squared is equal to 0. And in this case, you get a simpler equation. It is right here written, I think. And well, you have to find what are the coefficients that appears, and they are indexed by partitions of k into this number of blocks. Every partition you weight by this number, and then you get this number, these coefficients. Okay, this is the example of how you construct infinitesimal things. One problem that is we have to work still is the problem of finding the right cohomology theory. I show you the construction with details, it's clear there is some cohomology theory behind this construction, but at the moment we can only describe it formally for the first degree. I mean, for degree 1 or maybe 2, but a full homology theory is not yet present. So this is a problem which is open here. Well, now let me try to explain quickly how you go to Lie algebroids and N-Lie algebroids, examples of N-Lie algebroids. I take a finite dimensional vector bundle over some manifold. Then Lie algebroid can be defined. There are other definitions, but this is a very quick definition and useful for my purposes. Just introducing the structure of a differential graded algebra on the dual of the sections. Okay, so here you use the standard product, you get a graded algebra, and if you add the differential, it's the same as this is what you call a Lie algebroid. Okay, it can also be defined as equivalently as a degree 1 vector field on this manifold when you change the degree of the fibers. You put a -1 degree on the fibers. And this should be a vector field with this property, that b squared is equal to 0. Well, with this definition, then it's very clear how to proceed to generalize things. You can, there are two generalizations. One is, for example, if instead of choosing degree 1, your vector field can be decomposed as a sum of components in arbitrary degree, then you get what is called an L-infinity algebroid. And if you, instead of choosing b squared equal to 0, you impose a higher importancy identity, then you get N-Lie algebroid. And here an important subtlety appears is that when I use this, I usually think of b as a differential operator. Then you have the composition of b squared. You think of it as b composed with b, right? But and then you might think that the generalization will be b composed with b n times, but this is not the right generalization. So here. The composition of vector fields is not the right generalization. You have to use a different product. I don't know if this is very standard notation, for this product. I think it is not, but I write it like this. This is the product from vector fields. And this, I think, was introduced, or sometimes called Wimber product, or it leads to a pre-Lie algebra structure on vector fields, but it's not the usual composition in the sense that I don't have, well, it's not the usual composition. Well, then I defined then N-Lie algebroid is using this composition like this. Okay. Well, in the simplest case, for N-Lie algebroids are the N-Lie algebras. When you have just a fiber over a point, and you just want to describe you exactly what is then a 3-Lie algebra. So then you have some kind of shuffle, some kind of permutations like right here, and then this is the identity that should be satisfied. It's a 3-Lie algebra. Okay. Yes, which is equivalent to say that the differential associated on the wedge product, on this wedge product, and of the Lie algebra, here you put the vector space. The differential associated to this, to the cube, is equal to 0. To the third power is equal to 0, but not exactly composition, but using this composition that I showed you before, this composition here. You think of the differential as a vector field, and then you use this composition. And then you get this. I'm sorry? No, I don't think so. No, I don't think so. Well, I have to think about it. Mm-hmm. Okay, we'll talk about this later. Okay. So, and I'll go to the infinity algebras, the generalization of infinity algebras. Then for infinity algebras, you have these products of all higher order products, of the tensor product of the vector field. And, well, you sum of these products and you get a co-derivation on the algebra of the full tensor algebra with the degrees modified by 1. Then the generalization for the infinity algebra will be to choose n compositions, well, the co-derivations. Well, for when you have 2, of course, you get the usual definition of infinity algebras. It's written like this. When you compose 3, for example, this would be the new identity for an infinity algebra. So it's quite a complicated identity. And in general, well, you have to write it like this, so using graph. So you can just define this set of graphs with L leaf and N internal vertices, like this. For example, would be examples with 16 leaf and 3 internal vertices. And then the condition, this condition, the nilpotent condition means that you have to sum overall products, or so overall graph with these conditions, and set it equal to 0. So you have to, for all graph satisfying this condition, you will have a diagram similar to this. And the condition for an infinity algebra generalized in this sense is that this will be equal to 0. And well, this is what I have prepared for today.
Questions? Yes.
Can you go back to the slides where you had the Maurer-Cartan equation with many terms? So there is actually a way to do this. How do you do the deformation theory of a type of algebra? Well, you encode it by an operad. then you coin, say, a quasi-free resolution of that operad. So this guy is an operad generated by something. In the causal case here, something is a co-operad. And now you look at the convolution algebra, which is Prelli algebra, from that co-operad to the endomorphism operad. Okay? But in your case, if you encode the notion of an N-dga by an operad, okay, you will get that the associativity relation is quadratic. So this part will be resolved by the causal duality. But the part where d to the n is equal to 0, you have to use the higher causal duality studied by Roland. Okay. So then what you will get, the space of generators seems to be some kind of an co-operad. The linear part will be an infinity co-algebra. Okay. So when you will look at the convolution algebra associated to that, this will give rise to a quite easy, I think, L-infinity algebra. And this is the Maurer-Cartan equation in that L-infinity algebra. So it should be that. Okay, and then by the general theory, you should get a cohomology theory which encodes your infinitesimal deformations. Okay, so it should be, it should give a way, and definitely it gives a way to do that. Well, one has to do the computations.
Okay. Very nice comment.
And well, okay, and this is a comment. I have a question. The question is, what about this AN infinity algebra that you had at the end? You have any example of that, or?
Well, we can construct examples also in the same way using deformation. I mean, for example, taking an infinity algebra and deform it to it, and find the deformation and to solve a 3 infinity algebra. Okay. But they are more. To my taste, a little bit artificial at the moment. I mean, for N-differential graded algebra, I think they are quite natural, these examples. But for infinity algebra, still we have to.
And if I can ask, since we have time, well, okay, again, if you think of an infinity algebra to be this natural structure which appears from the operatic resolution of S, okay? You want to have a certain homotopy transfer theorem from DGA, what you get is an infinity algebra. What about this algebraic structure? Do you have an operatic interpretation of it?
Yes. We have an operatic interpretation of all these structures. Actually, the original way we described this definition of infinity algebra was through operats. I mean, using operats. Yes. So there is a construction, operatic construction.
Can you say more about this?
Well, yes, I can say more, but this is not so difficult to define. I mean, basically you need 2 operations, which are the product and the differential. And as an operand, well, you do the free operand generated by these things, the free operand generated by these 2 operations, and then you quotient in the category of graded vector spaces, and then you quotient by, well, the 2 natural conditions, which is this and the Leibniz rule, like this one. So then the problem is to try to understand this operand in more concrete terms, but this is the general definition of the operand that controls these N-differential graded algebras. And then for infinity thing, then you have to put more operations, all degrees, and well, you keep this condition, and you have to also do some generalized Reinich rule. That not only takes care of this term, but the other higher terms also.
This is the operand which encodes that type of algebra.
Yes.
Do you have a nice universal property that these guys satisfy, say, in the world of operads?
No, I don't think so. No.
Other questions? Same question?
No.
I already answered your same question.
He took the question from me. He stole my question. No, the next, the following question is, can you talk about the RAM N complex?
Well,
I mean, does it have a meaning?
Yes.
I
Let me show you this.
Given an algebra A, commutative or non-commutative, can you formulate something like an N-dga?
Well, this is what I can do. I mean, for any affine manifold is a very strong restriction, not for arbitrary manifold, but for affine manifold, I can define what is the rank complex of depth n. Okay, and this the rank complex has this nilpotency. This this number differential graded algebra. This is what I can do, but only for affine manifold, so it's very restrictive. Yeah.
Okay, if there's no other comments, let's thank the speaker again.